All right, we are now recording. Class has begun. Okay, so any questions about anything that you might have? I always ask that question. Nobody ever has any response there. So, okay, well, let's just go ahead and move on into the fun stuff. All right, so this week we're only going to meet on Monday and Wednesday, like I did last week. I think we've covered enough of the material. We don't need to keep meeting 3 times a week. Two times is going to be fine. And in fact, we might even cut it down to 1 time per week pretty soon. But for right now, keep planning on twice a week until I tell you otherwise. So we'll meet today and Wednesday, but not on Friday. Okay. Also, I looked at the Rube Goldberg machines that you had submitted as of last night. If any of you submitted some this morning, I didn't see those, but you know they were due on Friday. So if you submitted them this morning, that's gonna count as a late assignment. But anyway, so I looked at them and they were very cool. Wow, you found some awesome Rube Goldberg machines. One thing I thought was interesting was 4 of you chose the exact same video. So I'm wondering how that happened. I mean, if 2 of you had chosen the same video, then I'd say, okay, it's just coincidence, but 4 of you chose the same video. So I'm wondering, was that the one that showed up at the top when you Googled Rube Goldberg machine? I'm referring to the one about the lemonade. Okay, so 4 of you submitted a Rube Goldberg machine for delivering lemonade, which it was a very cool one. It's just funny that 4 of you did it. 2 of you submitted the same video for passing the salt. Some guy says to his friend, "Hey, can you pass the salt?" And then there's this incredibly complex machine for delivering the salt. One of you submitted the companion video for that, where this is the same guy, but this time he says, "Can you pass the pepper?" So that was cool. So yeah, I'm a lot of really interesting Rube Goldberg machines. So I hope that it gave you some inspiration for what you're going to make for your Rube Goldberg machine, because that will be the final exam in this class, which will be to make a Rube Goldberg machine. We're going to talk about that more later today. But I hope that you've been thinking over the weekend is, what could you do? What could you do? All right, so let's, before we talk about that, let's talk about the test. So yes, so Danny, in answer to your question, yes, I will go over the requirements today. Okay, but first we got to talk about last time's quiz. Okay, so what are bevel gears? Well, hopefully you guys all remember what those are, because there's lots and lots of different types of gears. So bevel gears are the ones that look like this, so that the teeth are at an angle, so that when you take a bevel gear and mate it with another one that is turned 90 degrees, then the full teeth will contact the full teeth on this one, contact the full teeth on this one. Because if you tried to do it using regular gears, it could work. I mean, you could have a regular gear that's like this and a regular gear like this, and they would work, but the teeth wouldn't interface completely. There would be only one little piece that would interface, and over time they would wear down very quickly. So bevel gears are definitely preferred to that. So I trust everybody got that one all right. Okay, rack and pinion. Okay, so I want you to think for a minute, what was a rack and pinion? What was a rack and pinion? Okay, hopefully you remember a rack and pinion is something that looks like this. Okay, so the rack is the bar that has teeth cut into it, and then the gear that interfaces with that is called a pinion gear. Okay, so where are they used? Well, only one of them is applicable, and it's the steering for cars. And this is what a rack and pinion system looks like from an actual car. The first one that I gave you, this one up here, that's just a generic one. This is one that's designed specifically for cars. And this is how it works. Okay, so you've got the steering wheel, and then the shaft comes down, is connected directly to the pinion gear. So when you turn the steering wheel, it pushes the rack, pushes it to the right or left, and that's connected to the wheels and causes the wheel to pivot. Okay, very efficient way of doing steering. Okay, what's the IMA of the gear train shown here? Okay, so we got to remember how do you calculate IMA? Okay, so the official definition that we talked about before is the ratio of the two distances. So when we're defining DE and DR, if we were talking about a lever, it would be the distance from the pivot point to the place where the force acts. But you could also define it to be the distance that your hand moves divided by the distance that the other thing moves. Okay, so Danny is suggesting that the IMA is the inverse of what we had talked about before, because before we calculated what was the spin multiplier, but the force multiplier is the inverse of the spin multiplier. Okay, so um, what I recommend you do is when we're talking about gears, okay, instead of calculating the distances involved, calculate the number of turns. Okay, so focus your attention on just these two gears for right now. So this is the handle that we're going to spin. And so we want to ask ourselves, if this axle were to spin one full revolution, how many revolutions would the other axle turn? And so you can see on the driver axle, we have an 8-tooth gear. So if one full revolution of the axle here is going to cause 8 teeth to move. And now the driven gear over here it's a much bigger gear, so 8 teeth on this guy is definitely not one full revolution. It's only a small fraction of a revolution, right? So if this guy is spinning one full revolution and this guy is spinning less, that's the same thing as if your hand is moving 5 feet, but the thing you're trying to move only moves 1 foot. Okay, so that means your force is being multiplied. Okay, so in this case, it's the torque we're talking about, because this is gears and spinning. So the torque is going to be multiplied. So the torque on the second axle here is going to be greater than it was on the first axle. Okay, so now you know that it's going to be the ratio of the teeth on one gear to the teeth on the other gear. So is it going to be the driven gear over the driver gear, or is the driver gear over the driven gear? Well, just since you know that the torque is going to be multiplied, increased, the force will be increased. So just look at whichever one of the gears has more teeth, divide by whichever one has fewer teeth. So in this case, the driven gear has 40, the driver has 8. So the ratio there is going to be 5. Okay, so 40 over 8 is 5. But that's just the ratio for just that gear pair right there. Then we have to realize that this gear here is also on the same axle as that one. So this guy now, he is no longer the driven gear. He is now the driver gear who is driving this gear. Now, both of those gears have the same number of teeth. So the IMA for that one's going to be 1. Which you might say, well, why bother if it's only 1? Well, it serves a purpose, because sometimes the gears that you want to put here just don't fit. And so, I mean, we wanted to put this tiny gear here, but if we tried that, maybe the axle would hit with the big 40 gear. Okay. All right. So the IMA for these two guys is going to be 1. And now we look at the last pair. So we got a 24 tooth with the 16 tooth. So in that case, the driver gear is going to spin 1 full revolution, and the driven gear is going to spin more. So in this case, the IMA is going to be a number less than 1, not greater than 1. Okay, so now that we know the IMA for each of the 3 pairs of gear, then we just multiply them together to get the total IMA, and it works out to be 3.3. Okay, so Danny is asking 5 times 1/3 equals 5/3 for the IMA. It's 5 times 2/3 here, not 1/3. Maybe that's the reason it's different. Yeah, this one here is 2/3, not 1/3. Okay, so when you multiply all the IMAs together, you get an IMA of 3.3. Okay, so now we're going to talk a lot today about IMAs. Pretty much all of it is going to be review, but I think it's going to be important review. One of the requirements that I'm going to tell you about for your Rube Goldberg machine is that you are going to have to calculate the IMAs for some of the simple machines that are in your Rube Goldberg machine. I'm not going to make you calculate the IMAs for all of them, because many things in a Rube Goldberg machine, IMAs are going to be difficult, if not impossible, to calculate. But some of the items that you include in your Rube Goldberg machine need to be simple machines that you can calculate the IMAs for. And so that's why we're going to spend the whole day today just reviewing how to calculate IMAs for various types of machines. All right, so hopefully you're good on gears now. Okay. Question number 4 from the quiz, what's the IMA for this one? So in this one, the simple machine is called a wedge. And again, the definition for IMA is always, you look at the distances. So what you want to do here is the distance that we move. So if we push the thing vertically 9.1 inches, how far horizontally is that going to push? So all you have to do is just take the ratio of the vertical distance over the horizontal distance, which is 9.1 divided by 10.8, okay? And it's always the distance that you move divided by the distance that the machine causes the object that you're trying to move. Okay, so in this case, our IMA works out to be a number less than 1. So our force is not being increased by this machine. Our force is actually being decreased by this machine. But, you know, sometimes that's okay. Sometimes you're able to exert a very large vertical force. All you want to do is redirect it. So you're changing the direction of the force from being vertical to horizontal. Okay, and the fact that the output force from this machine is less than the input, you know, that's okay a lot of times. All right, I'm not seeing any more questions, so I'll keep on moving. Okay, the secret phrase, okay, we knew that one, mousetrap. Okay, so let's do a little bit more review here. Let me pick a couple other things. So here is a pulley system, and this is the exact same picture that I showed you before, but it wasn't the best picture. So what I did over the weekend was I spent some time trying to find a picture that helps you to understand better what's going on. So what you see now, this pulley system is the exact same pulley system as here. It's just that instead of looking at it from the side, now we've twisted it just a little bit so that you can get a better picture of what's going on. Okay, so this is a block and tackle where the upper part here has 2 wheels that the ropes can go around, and the lower part only has 1 wheel. And in fact, I even found another picture that helps you understand better still. So this is a close-up view of the upper part of what I just showed you. And it's got all the names for it. Don't worry about it. I mean, if you were a sailor, you need to know these names. But for what we're going to do today, all you need to know is that this inner part here, this little roller, this is where the rope is going to go. And in fact, here is an actual one. Now this guy, he just only has 1 roller in it, whereas the thing you see on the screen has 2. But so if you put it like this, if you take the rope and you put the rope over the roller and come down here, okay, so this is a simplified version of what you see a picture of. So these rollers here, those are called sheaves, okay? So the system that I showed you up here, okay, this one where you've got 2 sheaves in the upper block, and you've only got 1 sheave in the lower block, okay? So now hopefully you understand a little bit better what's going on. Okay, so I want you guys to look at this and think, okay, what is the IMA of this block and tackle system, which, by the way, is called a luff tackle. But again, that's just a trivia name. If you're a sailor, you need to know about this because, boy, sailors use this all the time. But I'm not going to require you to know this a luff tackle. Okay, so David is saying that the IMA is -3. Does anybody else want to chime in? Somebody agree with him? Somebody disagree with him? I need at least 1 more response. Okay, so Van is agreeing with him. Okay, and in fact, I also agree with him. Okay, all right, so the IMA in this case is going to be 3, and the way that you know it, okay, so Danny's question is, how do you find it? Okay, I'm glad you asked the question. Okay, so the way you find it is you draw in your mind a little dotted box around the pulley that is attached to the weight that you're trying to lift. So this what you see right here, that's the weight that we're trying to lift. And this is the block that's directly attached to that. And so, yes, David, you got it exactly right. Now all you do is just count the ropes. Okay. So if you pull on a rope, we're going to make the assumption that the tension in the rope everywhere is the same. So if I pull on this part of the rope right here with a force of 10 pounds, okay, we are going to assume that everywhere in the rope now there is a tension of 10 pounds in that rope. Now that assumption is only going to be true if our pulley system is completely frictionless. Okay, but that's what IMA means, right? The I in IMA stands for ideal, which means frictionless. Okay, so if we pull with a force of 10 pounds, that puts a tension of 10 pounds everywhere in the rope, and we've wrapped the rope here so that we've got can't count. We got three strands right here. Each one of those strands has a tension of 10 pounds in it. So that means that there's 30 pounds pulling this guy up. And so that means our weight here is going to feel a force of 30 pounds pulling it up, but we are only pulling with 10, okay? So by counting the ropes, we can calculate that the IMA is 3. And so I see the question here, why is it negative? Well, because we are pulling downward. But the thing that we're exerting the force on, that's experiencing an upward force. So that's where the negative comes from. So if we pull downward and our machine ends up pulling upward, okay, then we put a negative in there. Okay, but don't be surprised if a lot of times if you were to go on Amazon.com or some other place that sells pulleys, and you say, I want a pulley system that has an IMA of 3, okay, you don't have to say IMA -3. They usually the people selling them, they leave out the negatives. Okay, so if I were to put this on a test and I were to say, what's the IMA of this machine? If you said +3 rather than -3, I'd let you have it. Okay, I don't want to be too much of a stickler there, but to be completely technically correct, we would say it's a -3. Okay, now here, what I've done is I've taken that exact same pulley system from before. So look on the right here. This is we got 2 sheaves up here, 1 sheave down here. So it's the exact same physical pulley. What I've done is I've just flipped it upside down. Okay, so the block here that only has 1 sheave in it, I've hooked it up to the ceiling, whereas before I had it hooked up to the weight. Okay, and then the block that has 2 sheaves in it, that's the one that I've now hooked up to the weight that I want to lift. So if it's the exact same block and tackle system, and last time just a few seconds ago, we calculated that the IMA of it was 3. So if it's the exact same system, would the IMA not still be 3? So I want you guys to think about it. What do you think, that the IMA is still 3, or do you think maybe because we've hooked it up differently, maybe the IMA might not be 3 anymore? So I need a couple people to type some in. What do you think? How many of you vote that the IMA is still 3, and how many vote that it's different? Okay, so I see one person is saying that it's 3, but looks like the majority of you are saying, no, it's not 3 anymore. It's 4 now. Okay, and Sky is exactly right. Sky is saying if you use the box method, then you're going to find out that it's 4. And so that's exactly what I'm going to do. I'm going to do what Sky suggested. So I'm going to look at the block that is attached to the weight that we want to move. Okay, and I count the ropes, and I see that there's 4 ropes here, not 3. Okay, so the IMA is not going to be 3 anymore. The IMA is going to be 4. So Danny, I like what you're saying. When in doubt, oh, I'm sorry. No, I read that too quickly. You're saying, wait, I'm in doubt. Okay, so yeah, it is weird, but you know, if you think about it, it works. Okay, all right. So so do not just blindly memorize and say, well, you know, if we got 2 sheaves up here and 1 sheave down there, that means IMA is 3. Don't blindly memorize that like that. Use the box rule. Draw the box around whichever of the blocks is attached to the weight that you want to move, and then and only then count the ropes. And by the way, you'll notice it's not a negative anymore. It's a positive 4 now, not a negative number. Why is that? Well, because now the way that we've got this working, in order for us to pull, we have to pull upward, and then the weight is going to experience an upward force. So both of them are upward. So it's not a negative number anymore. Now it's a positive number. Okay. So make sure you guys get good about how to calculate IMAs. All right, now here is another pulley system, but this time my upper block has 3 sheaves. My lower block has 3 sheaves. Now, if you were a sailor, you would call this arrangement a threefold purchase, but I'm not going to worry. You don't need to worry about that name. So use the dotted box method, count the ropes, and tell me what's the IMA of this pulley system. Okay, so I see one person says 6, another one says -6. And so -6 is the more correct answer, but I would give you credit if you just said 6. Okay, so yes, the IMA for this case is going to be a -6, but if you said 6, I'll give you credit. Because most people don't worry too much about the direction. Most people just worry about the magnitude of the IMA. Okay, so I'm trusting that you guys are now good with pulley systems. So let's move on to something else that might look like a pulley, but technically it's a different machine. Anybody remember what the name of this particular simple machine is? I'll give you a minute to type something in. Well, yeah, it is a well, I know, but this particular thing, okay, wheel, but you only got half of it. The other half is axle. This is when you take a wheel and an axle and you put them together, okay? Okay, so what you do is the person working the machine, you grab onto these little handholds here, and you are going to pull the wheel, which has a large diameter. And this large diameter wheel is attached to an axle, which has a small diameter. Okay, so that allows you to pull up a heavy bucket full of water or whatever using a lot less force than you would have to if you just grabbed onto the rope and pulled the rope up. Okay, so in this case with the wheel and axle, the IMA, if you look it up in books, some books, they'll tell you take the radius of the wheel divided by the radius of the axle. And other books say take the diameter of the wheel divided by the diameter of the axle. It's the same. And don't be surprised, you might even say some books that say take the circumference of the wheel divided by the circumference of the axle. They all work out to be the same. Okay. All right, so let's do an example like you might see in a quiz, wink, wink, nudge, nudge. Okay, so I've done diameters here. Okay, good. I see you're way ahead of me. I'm glad to see that. Okay, so the diameter of the wheel is 36 inches. The diameter of the axle is only 12. So just take the ratio of those two. And so that means the IMA of this particular machine is 3. So that means if we had a really big bucket that had a lot of water in it, so that, let's say it weighed 100 pounds. So if we tried to lift it, if we try to just pull the rope by hand and just pull straight up, let's say it's a really big bucket. So it's 100 pounds of water, more than we want to do. Hook it up to our wheel and axle, and we can lift that 100 pounds of water using a force of only 33 1/3 pounds. Okay. So this is the same problem that we had on the quiz last time, but I noticed that when you guys took the quiz, I noticed that several of you took it several times, which is allowed. I mean, I purposely set up Canvas to allow you to take it multiple times. That wasn't a mistake on my part. I did that on purpose. But the thing is that Canvas records every one of your attempts. So when I went and I looked at it, I saw that several of you had taken the quiz multiple times before you finally got a perfect score on the quiz. And I went back and looked to see, why did you take it multiple times? Well, it was because you had missed this one. Okay, so that tells me that you obviously need a little bit more of a refresher on this. Okay, so if you have a ramp, remember the formula for IMA is the ratio of the distances. And in this case, it's the distance that your hand moves if you use the machine. So in this case, that would be 5, divided by the distance that your hand would move if you had not used the machine. that's a good way to think about it, okay? So the vertical distance was 3, so that's all we care about. The horizontal we don't care about. So the ratio is going to be 5/3. Okay, and so apparently some of you were a little unsure of that. Okay, so the multiplier here is going to be 5 divided by 3. Okay, which works out to be, let's see. Okay, all right. So it's that. Okay, so now that we know the IMA, then we can answer the question. So the question, it says, if our input force was 480 newtons, then what would our output force be? So we just take the 480, multiply it by 5/3, which is our IMA, and that gives us our output force. Okay, so our output force there turns out to be 800. Okay, all right, and I see Sky was way ahead of me on that, so good for you. All right. Okay. All right. Now, levers. Levers, most people are pretty comfortable with, but you do have to be careful because first-class levers and second-class levers, they behave a little bit differently. Okay. So let's suppose that I were to give you a quiz here where I've defined these distances here. So this distance here is 12 feet. This distance here is 3 feet. So most people have no trouble if it's a first class lever. Okay, remember first class, second class, third class. Okay, so let me just ask the question. Some of you probably already started typing. Just look at the first class lever only. What is the IMA of the first class lever going to be? The one on the top. Don't look at the others. So I hear somebody saying 4, somebody else. Okay, looks like everybody agrees it's 4. Okay, and so if we look at the IMAs, it's the effort distance over the resistance, the effort arm over the resistance arm. Okay, so the effort arm is 12, resistance arm is 3. So take the ratio of that, and yeah, I get the same number you guys got. Now you guys left off the minus, which is perfectly okay. Don't worry. I mean, I like to be 100% correct, but I would not mark you wrong if you said 4. Okay. Now, what about the second class lever? I mean, this distance here is still 12 and this distance here is still 3. So would the IMAs not still be 4, or would the IMA be something different? Okay, so I see Eve says that it's going to be 5 now. And some of you are saying 1/4. And then, okay, now you said, wait, no. Okay, and so Sky says, okay, let's go back to the definition here. Sky is saying, we take the distance of the effort force, which now, can you see here, the effort force is the distance from where we apply our force to the fulcrum, and that distance is not 12 anymore. That distance is now 15, okay? So by taking the fulcrum and moving the fulcrum over here, we have changed the effort distance. It's no longer 12, it's now 15. Now the resistance distance is still 3. That, okay, so it is 3 to the right, here is 3 to the left, so it's still 3. But the effort distance is not 12 anymore. The effort distance is now 15. So that means our IMA went from 4 to 5. Actually, -4 to -5, but I'm not going to worry too much about the negatives. So yeah, the IMA now is increased. So this is an interesting thing that a lot of people don't realize. Let's say you've got a bar. So this horizontal line here, this is a big metal bar, and you want to use that bar to move some heavy object. So you could either use it as a first class lever or a second class lever. The second class lever will give you a bigger IMA than the first class lever would. Okay. So why is it negative for the second class lever? Okay, well, my effort, oh, wait a minute. Oh my goodness, oh, you are right. It's not negative because we are pushing up and then the output force is up. Oh my goodness gracious. Let me go in and fix that. You are right, it's not negative. Are you guys gonna make me wear the wig because of that? Oh, okay, yeah, let's see, the wig's in the other room. Hang on a sec, I'll go get the wig. I deserve it. Hang on a sec while I go get it. Okay. Oops. I have to put this on first and the wig second, otherwise it doesn't work too well. Okay. Okay. All right. Yeah, I earned it. I deserve it. Okay. All right. So calm down. Am I upset? Or are you saying it to yourself? Okay, let's move on. Oh, you're saying it's Danny. Okay, gotcha. Anyway, okay, now, all right, so how about the third class lever? Okay, all right, so the third class lever also should not be a minus. Oops, let me go back up here. Hang on a sec. Let me fix that on here, and I also got a copy of it up here. Okay, all right, yeah, so there we go. Okay, so the third class lever, our IMA is a number less than 1. Okay. So with the third class lever, it's not increasing our force, it's actually decreasing the force. Okay. But the advantage there is that it's increasing the distance that the end of this thing moves. So if you look over at our arm here, you can see our bicep, which is a lot stronger than people realize, okay, but it can only move over a short distance. So the bicep allows the hand to move a big distance. Okay, so third class levers are in fact very useful. He's strong. Okay. All right. Okay, now let's get back to talking about the Rube Goldberg machine that I want you guys to design and build and take a video of, and I want you to submit the video. Okay, now here is the requirement. 3 of the elements in your Rube Goldberg machine need to be simple machines that you can calculate the IMA for, and you need to actually calculate the IMA. Okay, so let's look at my example Rube Goldberg machine right here. And notice that they've put numbers on each of the elements, which is something I want you to do too. So element A is an alarm clock. So when the alarm clock rings, it starts vibrating. Okay, well, kind of hard to calculate the IMA for that one. Now it's okay for you. It's okay for you to include elements in your Rube Goldberg machine that don't have easily calculatable IMAs. It's okay to use them. Okay, but 3 of them have to be ones that you can. Okay, so the alarm clock here is perfectly valid to include, even though we can't really calculate the IMA. Okay, so the second one is we got this little ball here, and when the table gets vibrated because of the alarm clock, it falls off into here. Again, that's one you can't really calculate an IMA for. So element B, okay to include, okay, but you just know IMA. Now, when we get to element C, here we have one that we could calculate an IMA for. So let's see how we could do that, okay? It's a wheel, which in this case, if you look at it, it's really acting like a lever, okay? When the ball falls into the cup, that exerts a downward force, which causes the upside down cup on the other side, causes that to move up. So this wheel here is actually performing the function of being a simple lever. And hey, that's something we can calculate an IMA for. And so I want you to do it. Okay, so in this case, what we're going to do is we're going to look at the distance from the fulcrum to where the force is exerted, which in this case I'm just kind of making up. I'm assuming that it's 6 inches. Okay, and then we have to calculate the distance from the fulcrum to where the output force is exerted, which in this case is going to be also the same. It's going to be 6 inches. So our IMA here is -1. Now, if you wanted to call it a +1, I'd be okay with that. All right. So bingo. So this is one of the 3 elements in my machine. Now your machine is going to be different. Okay. All right. So I've calculated the IMA for one of my elements. Good. I've satisfied 1 out of the 3. All right. So let's continue on here. So in this thing, when this little cup here flips up, it knocks over the cup, and the ball comes out. So I'm thinking, I don't know how I'd calculate the IMA for that. So then the ball comes over here and rolls off into there. So again, kind of hard to calculate an IMA for. But now, once we get a weight in the cup, that weight is going to pull down on this end of the scissors, okay, which is going to cause the other end of the scissors to come up and cut the string. Hey, I'm thinking we can calculate the IMA for that. All right, so let's focus our attention over there. Again, we have just a simple lever, just a first-class lever, okay? So supposing the distance from the pivot point to where we tie the string on is 2 inches, and supposing that the distance from the pivot point to where the string gets cut is 7 inches, then we say, okay, I know how to calculate the IMA for that. That would be an IMA of 2/7, which is a number less than 1. So in this case, we're not increasing the force, we're decreasing the force, but that's okay. That's a valid machine. So the IMA for this guy is going to be -2/7. So good. So now I've calculated the IMA for 2 of the elements in my Rube Goldberg machine. I just got to go one more. All right. So let's see how I could go one more. Okay, so when the string gets cut, the shoe falls. Now, if the shoe were to fall at the end of the stapler, so the effort force is the shoe falling. The output force is the stapler stapling. Both of them are going to be the same distance from the pivot point right here. Okay, this is, I hope you guys can see where I've got my cursor moving. Okay, so in this case, again, my IMA is going to be the effort force over the resistance force, which is going to be 1. So again, I have another IMA of just 1. Okay, and so in that case, you'd say, well, that's kind of boring. Okay, maybe boring, yes, but still valid. Okay. Now, the picture here that makes it look to me like that's what's happening. It looks to me like the shoe is hitting right at the end. So if that's the case, the IMA is -1. Now, if I wanted to make it a little more interesting, I could arrange things so that the shoe doesn't hit at the end of the stapler, but instead the shoe hits at the middle of the stapler. Now, that's not what it looks like is happening here. But if I wanted to make it more interesting, I could make it that way. And so in that case, my IMA would be 1/2 rather than 1, okay? All right, so I've got the 3 elements of my Rube Goldberg machine, which I calculated the IMAs for. So I have satisfied the IMA portion of the Rube Goldberg assignment, okay? Now, I would hope that in your Rube Goldberg machines, you have more than just 3 elements. In fact, let me rephrase that. I will require that in your Rube Goldberg machine, you have more than 3 elements. I'm not going to put an upper limit on the number, but I will say, I mean, don't go too crazy on this. I don't want you to spend unbelievable amounts of time. I don't want you to spend 50 hours making a Rube Goldberg machine. That's too much, okay? I'm not going to give extra credit for making a super, or will I? I don't know. What do you guys think? Some of you desperately need extra credit. Maybe I should offer it. So what do you think? What do you want? Do you want me to offer extra credit if you go over and above and you make a super duper Rube Goldberg machine that has lots and lots of different elements in it? Would you like it for me to, if I offer you extra credit for that, or would you say no? Okay, so it looks like most people are saying that they would like it. Okay, all right, well in that case, that's what I'll do. But I'm not going to give a ton of extra credit, okay? So let's say that the amount of extra credit that I would give would be no more than the amount of credit that you would get from 2 quizzes. So, okay, so each quiz is worth 10 points. So I'm going to put an upper limit on it. I'm going to say the maximum amount of extra credit that you can get is 20 points, okay? So that makes it worthwhile spending a little bit of extra time making a really nice Rube Goldberg machine, but it doesn't make it so that it's worth spending like 50 hours or 100 hours. It's not worth that much time, okay? So don't go sinking that in, or don't go using that much time. Okay, so Danny is saying, when is the thing due? Okay, so here is what I'm going to say for that. I'm going to make it in parts. There are going to be different milestones. Okay, so on Wednesday of this week, I want you to submit what you intend to do for the 3 elements of your Rube Goldberg machine that have calculatable IMAs. Okay. Now you don't have to actually build it by then. All you need to do is submit drawings. Okay. So and what I want you to do is just, you can draw it out on a piece of paper if that's easier for you, and say my first element is going to be this, and here's the IMA for it. My second element is going to be this, and here's the IMA for it. My third element is this, and here's the IMA for it. So just draw them out on paper, take a photograph of it, and then upload the photograph to Canvas. Now, David is asking, is it okay to CAD it? Yes, absolutely, positively. Now, should I give extra credit if you CAD it? No, I don't want to go crazy on the extra credit. What I will say is, I will say attaboy. Okay, if you CAD it up, I will look at it and say nice job, but I'm not gonna give extra credit for it. Okay, so all right, so that's what's going to be due on Wednesday of this week. So 2 days from now, I need you to tell me what you plan to do for the 3 elements in your Rube Goldberg machine that have calculatable IMAs. And I want you to actually calculate the IMAs. Okay. All right. But you don't have to build anything. Okay. So, and then we're not going to meet on Friday. So on Monday of next week, so 1 week from now, I'd like you to just write up a progress report of how you're coming on your Rube Goldberg machine. I don't expect you to have the entire thing built by Monday of next week, but I do expect that you will have started on it, okay? So I want you to write up and say, okay, here are the elements that I have built so far, and here are the remaining elements that I intend to build. Okay, so the only thing that's due on Monday of next week is just a progress report. And then on Wednesday of next week, do you think that that would be a good deadline, or would you prefer to have it be Monday 2 weeks from now? Maybe that would be a better way to do it. Yeah, I think that would be a better way to do it. So what do you guys agree? So if I say 1 week from now, I need a progress report, and then 2 weeks from now, that's when the final thing is due. Does that sound like a reasonable requirement? Okay, good. All right, you guys are agreeing. So, if we do it that way, then maybe on Wednesday of next week, there's no need for us to even hold class. So let's do that. Okay, so we're going to meet on Wednesday of this week, where I want you guys to have submitted your 3 elements. And what I intend to do on Wednesday of next week is I intend to talk about those, give you some feedback on those, and maybe introduce just a few more new concepts, but not much. Okay, so we will meet on Wednesday of this week. We will also meet on Monday of next week. It'll probably be a pretty short meeting. I just want to, by that time, you should have submitted your progress reports. And so I want to give you guys some feedback on your progress reports. So we will have an online class on this Wednesday and also on next Monday, but we will not have an online class on Wednesday of next week. And then the final reports will be due 2 weeks from today, or reports is not the wrong word to use. 2 weeks from today, that's when I want you to submit a video of your Rube Goldberg machine. Okay, not just a report, not just a photograph, but a video of it working. Okay, so I think we've clearly defined everything. So I'm going to call it good here. Okay, so here is just in writing what I said before. Okay, so 3 of your elements must be ones for which you can calculate IMAs. And I want by this coming Wednesday, I want you to tell me what those 3 elements are. I want to see drawings of those 3 elements. You don't have to actually have built them yet, just your drawings. And I need to know what you calculated the IMAs to be. Okay, so Dan's is saying, are we allowed to incorporate electronics in your machines? Yes, that would be great. I would enthusiastically encourage that. Yes. Okay, so are there any other questions? Okay, so don't forget to take the daily quiz for today. The daily quiz will be, I'll give you a couple of simple machines and I'll ask you to calculate the IMAs for those machines. Okay, so it should be relatively straightforward. Okay, so Luke is saying for the levers, wouldn't the IMA slightly be less because the angles and such with the lever rotating around the fulcrum? Yeah, Luke, you are correct. But that's a little bit more complex than I want to get into. Remember how we said that when you're exerting a torque, the actual torque is not just force times distance, it's actually force times distance times the sine of the angle. Okay, so so calculating the IMAs, so Luke, you are correct in what you say, but I don't want to go to that level of complexity. So don't worry about that. So Luke is saying it should be the cosine, not the sine. Depends on which angle. If it's the angle, well, I tell you what, Luke, let's have this conversation one-on-one. But basically, there are a couple angles you can measure. So if you measure the angle that physicists use when they define it, then it turns out to be the sine. But if you were to measure the complement of that angle, then it would be the cosine. But let's not go into that. Okay, that's a level of complexity that I don't think is worth going into. Okay, so I don't see any more questions other than that. So let me go into my normal going once, allowing for questions, going twice, still see no questions. Oh, a question just came up. Oh, secret phrase, yes. Good question. I forgot about the secret phrase. Okay, so David, oh, okay, you want it to be Gerb. Okay, well, Luke, I actually like Luke's better, but David beat us to the punch. So we'll go with that. So G-U-R-B. Okay, so there we go. G-U-R-B, that is the secret word for the day. What is backwards? Ah, okay, so that's why he likes it. Okay, good. All right, so that's the secret word for today. Okay, so again, the birds are fake. I have no idea what birds you're talking about. Okay, so going once, going twice, sold,